So hello everyone. Today is the first lecture for the atomic physics. Means today we are going to start it. And in this we will study about the atomic and the molecular physics. So we will study them separately. First the atomic physics, then the molecular physics. Then we will study about lasers. So this whole syllabus combined to the 15 marks in the exam. So there will be very simple question will be asked from these sections. So if you study it properly, then you will definitely get these 15 marks. So if any book you want, then I can recommend you for the atomic physics is by White. And let's start. First, let's see the syllabus for the atomic physics. So, first we will study about the Bohr model. Then we will study the Sommerfeld model. And these models are for the means different spectroscopies we get means for the hydrogen atom. So these models will be used to explain them. Then X-rays, orbital angular momentum, spin angular momentum, magnetic moments, space quantization, Larmor precision. Then we will study about the spin orbit coupling, relativistic correction, fine structure, Dirac's equation, Lamb-Shift. Then we will study about the couplings, LS coupling, JJ couplings. So there are most of the topics you will find in the quantum mechanics also, but we will just confine to these. Zeeman effect, then normal and the anomalous we will study. Then we will go to the Paschen effect, hyperfine spectra. So here the atomic physics will end. Then we will go to the part B, that is molecular spectroscopy, in which we will study about the different spectroscopy like rotational spectroscopy, vibrational Raman, and some extra topics will be there. So we'll study them also. Then there will this part C, which include the lasers. So that's how we will go. So let's start with the part A, that is Bohr model. So to study the Bohr model, first we need to understand the hydrogen gas. And to understand the spectroscopy, we took the very simple gas, that is hydrogen gas, which has only one electron in its orbit. So if you excite the hydrogen gas, then it will emit radiation. This is the observable thing which you can observe. And then you can see that using the spectrometers, we get some spectrum. Means there is some bright lines in the dark. So that is called the emission spectrum. And if you see that there is some dark lines in the bright, that will give you the absorption spectrum. But we will study about the emission spectrum here. So using the spectrometers, you will see that from the radiation there will be some particular lines which are bright. So these are the actually the emission spectrum and made of various wavelengths. Mean each bright lines representing the different wavelengths which are emitted. Means only the particular states are getting excited. So that's why we are getting the different wavelengths. For the better understanding, you must see some images on the Google. There you can see the spectrum of the hydrogen gas. There you will see that there are some black dark and there is some bright lines. These are called the spectral lines, and each correspond to the each wavelength. Means there is some particular wavelength range which correspond to a particular line. So that is called a spectral line. And this family of spectral line is called the spectra, that is atomic spectrum. So I refer to you that must see the images for that. So by passing electric current through the hydrogen gas, we can excite it that. One can create excitation in the gaseous atoms. These atoms in excited states jump to the lower excited states or ground state automatically. After some time in this process, radiation is emitted, which consists of various wavelengths. When studied through spectrometers, each of these wavelengths component of radiation is called the spectral line, and complete family of line is called the atomic spectra or line spectrum of the hydrogen gas. The hydrogen gas spectrum consists of 5 different families of spectral lines. See, when there was these spectrometers are under development, then we have only these 5 spectral lines families we get. And when there is means revolution in the spectrometers and we get the higher resolution, then you find that in these 5 set of families there are multiple lines inside that also. So that's how these things go on. Now we have only the 5 families, means there was this dark and there was this 5 bright lines, and that consists of the 5 different families. So the names are given to these families, that was Lyman, Barber, and Paston, Brackett, and the Fund series. So the first series is Lyman series. So we'll study them. Means you have this dark and there are the bright lines. So there will be these particular families. So these families are include these 5 series. So we'll study them separately. So for the Lyman series, you will see there are different energy states in the spectrum and for the atom, and you will see that all the when the electron is jumping from the higher states to the first excited states, then you will get the Lyman series. And it is going like it can go from 2 to 1, 3 to 1, 4 to 1, and 5 to 1 for the infinity to 1. That's how you will get different wavelengths or different frequencies, and that will give you a particular set of lines, and that is called the first family, that is Lyman series you will observe. And for the minimum wavelength, you know that for the minimum wavelength or the maximum frequency, that are the same things, you have to get the maximum energy. So maximum energy, when we this n is tends to infinity and it is dropping from infinity to 1, then you will get the maximum energy, and that will give you the minimum wavelength. So this formula was given, means just to remember this formula. We will come to this, that how this formula is derived. But now just remember this formula, that this formula gives the all the wavelengths which required for the Lyman series. When this nf is just put it equal to 1, means all the initial final stage is 1, but initial can be 2, 3, 4, 5, 6 to the infinity. So this will give you the lambda for the Lyman series, all the wavelengths. So it can go from ni equal to 2 to 1, 3 to 1, and 4 to 1. So all these three lines are given some names, means first is called the L alpha, L beta, and L gamma. So you must remember, sometime in the question it is given directly that it is L alpha and L beta and L gamma transition. So you must remember it is 2 to 1, 3 to 1, and 4 to 1. So this is the formula. Now ni can go from 2 to infinity. So the minimum wavelength, when it will be minimum wavelength, when this energy difference is maximum. So for n equal to infinity, initial should be infinity. This will give you 0, and lambda will be 1 square by r. Now r infinite, what is this? This is called a Rydberg constant. So you must remember the value of this Rydberg constant, that is 1.097 into 10 to the 7 meter inverse. And 1 upon r infinite will give you 917.4 angstrom. So this is a very important result which you can use in the calculation, very fast calculation you can do. Means this simply, if you need to find the for Lyman series the minimum wavelength, just this will be 917.4 angstrom. So that's how you can write directly. So you must remember this result, very important. Similarly, if transition is to the second state n equal to 2 from the upper higher states 3, 4, 5 and infinity, then you will get the particular wavelengths, and that wavelengths will lie in the Balmer series, that is the second set of family. The first in the history book, if you see, this series was first discovered, and in all these series, first series was this, because this is lying in the visible region, and this will be more easy to observe as compared to other the infrared and the ultraviolet region, because you can't just simply see this ultraviolet region lines, but you can see these visible lines. That's why this was the first series, and the formula was first discovered for this, then it was applicable to all these. So just like in the Lyman series, you can formulate it also, like 1 upon lambda equal to r infinite, 1 upon 2 square minus ni square. So final state should be 2, and ni can go to the infinity. So again for the minimum, ni should be infinite, so it will be 0, and lambda will be 2 square by r infinite. So must remember, now 1 upon r infinite simply 917.4 angstrom multiply 2 square will give you lambda minimum for the Balmer series. So that's how this result is very helpful, must remember. And again there was names given to these lines for the Balmer series also, like in the Lyman series, L alpha, L beta, L gamma. So for the 3 to 2 it is H alpha, 4 to 2 it is H beta, and 5 to 2 it will be H gamma. So must remember these names, it will be helpful in the questions. Next is for the Paschen series, means final state will be 3 and initial will be go to the infinite, 4, 5, 6 to infinite, and it will lie in the infinite region. So lambda minimum will be n I equal to infinite, so lambda will be 3 square divided by r infinite. So this will be your minimum wavelength. And just like the bracket series, this is also lying in the infinite region. Then nf equal to 4 square ni square, and you can calculate the ni, and the minimum will be 4 square by r infinite. And similarly Fund series, it is also lying in the infinite region, and you can find the same formula for this also. Final state will be 5 and initial will be 6, 7, 8 to infinite, and lambda minimum will be 5 square by r infinite. Now see, these are the results which we observe. But to explain all these, that why we are getting only certain bright lines, not all, everywhere. So this was means there were different models for this to explanation of this, but there was very much efficient model was Bohr model, because that explained everything here. Means that was very peculiar model which still are in the use. Means still we are taking the advantage of that. That's why the Bohr model we will study. So in the Bohr model, what he did, it was a semi-classical model, because in this, why we are calling it semi-classical, because here in this model we use the classical results and the quantum mechanics results or the modern results also. That's why we call it as a semi-classical model. So Bohr produced semi-classical model for explaining various families in hydrogen and hydrogen-like atoms. This model was a combination of classical ideas mixed with the quantization idea. That's why this is called a semi-classical model. So in this model we also introduce a quantization which is different from classical. That's why we call it as a semi-classical model. So we'll study that how it is semi-classical and how it is quantization introduced. So for that we must know the postulates. The classical equation of motion are applicable for electrons in atoms. However, means you will see that classical equations like angular momentum or the velocity and the F equal to ma, these equations are valid for the electrons in the atom, but only discrete orbits are defined. Means electron can go around the atom like it is rotating with the angular momentum and it is fixed, but the energies, means different energies, it can take the continuous states according to the classical mechanics, but there is this quantization introduced that it can take only particular energies around the atom. So that was the quantum thing, that's why it is called the semi-classical. So the classical equation of motion are applicable for electrons in atoms. However, only certain discrete orbits with certain energy are allowed. These levels are called the energy levels of the atom. So that's why this is a mix of quantum and classical. Motion of electrons in these quantized orbits is radiationless. Means you will see that these are the postulates. Why? Because we know when electron is rotating around the atom, it is going into the changing direction, means velocity is changing at every point, means it is accelerating, and accelerating charge must give the radiation. But here this is the postulate said that when electron is rotating around the atom, then it will be radiationless. However, when these electrons, means there will be no radiation when electron is rotating around the atom, but there will be radiation when it is jumped from the higher state to the lower state. So this was the postulate from the Bohr. However, when these electrons jump from the higher to the lower, then they emit radiation of particular frequency. Means you will say that n dash is higher state, then n is will the lower state. Then energy difference will give you the energy of the photon of the radiation. So you can find the radiation energy, that will be minus E and S, that is the higher state, and these are the negative because you know these all electrons or the states are bound, and bound state will give you the negative energy. So it will be the minus E and S, that is the higher. Means if you go to the above, it is like minus 13.6 and minus 13.6 by 2 square until it is becoming less negative, and when it will at infinite it will become 0 and positive, that means it is not bound anymore. So now you can find the frequency at every point by this formula, means higher state minus the lower state, that will give you the energy of the photon, and from here mu will be equal to this difference divided by h. So this is the initial minus final, so that's how you can find the value. So now these E and S are the absolute values, so you will just take the difference and divide by h will give you the frequency. Because we already take the sign convention here, that's why these are the absolute values. Now, out of the infinite possible orbits available for electron for revolving around positive charge nuclei, only those orbits are possible for which, means this is again the third postulate, means there were infinite orbits as I said, but the energy is fixed, means only the particular energy can take by the electron. So for that, there will be only particular orbits should be taken by the electron, and if orbits are fixed, then means angular momentum of that particular orbit will be fixed. So for electron for revolving around positive charge nuclei, only those orbits are possible for which angular momentum magnitude will be nh by 2 pi. So only these values of angular momentum will be given. Means you know if anything is rotating around some particular object, then that angular momentum is constant of motion, means that will remain same. So only these values will be given, means only these orbits are permitted. So n equal to 1, 2, 3, 4, that's it, how it will go. And this is called the quantization of angular momentum. And how Bohr come to this result? Because he was studying the de Broglie wavelength and all, so he just taken that when electron is rotating, it is also having the wave nature, and it must complete this complete cycle, means it will be complete cycle. So that's how he give this result. So in the next lecture we will see some formulations based on the Bohr model, and we will also see the proof of this, and then we'll go to the Sommerfeld model. So that's all for today. Thank you everyone.